Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 3.3, 3D vector planes. It's not easy to define a plane on a 3D volume or space, but there are two ways of doing it. One of them is using the Cartesian equations, which is denoted from the bottom. n1x plus n2y plus n3z plus d equals to 0, where n1, n2, and n3 are the respective x, y, and z components of the normal vector. A normal vector is defined to be the perpendicular vector to any vectors lined on top of the plane. So if I have a plane like this, the normal will point upwards, and the length doesn't matter, and where it starts doesn't matter. As long as it's a plane, a 2D plane, it's flat, and therefore the normal vector is a constant value on any point on the plane. This can also be defined using vector notation, or take a dot n is 0, where a is a position vector, a certain point a from the origin, which goes, this is the vector a, then r is the vector perpendicular to or on top, lying on top of the plane. So this is an arbitrary vector r take a. Right. So r take a can be in any orientation on the plane as long as it is perpendicular to the normal vector, which also by definition lie on top of the plane. So r take a is just a point r this way. So r is a position vector, a is a position vector, so we've got two position vectors, and if we take the difference, we essentially find that vector connecting those two lines. A take r or r take a doesn't really matter because they are just directions. The important bit is the dot, because it is in normal form, dotted with the normal equals to 0. It's defined to be perpendicular to the normal vector. So as long as a is on the plane, r take a dot n will be 0 if r is on the plane as well. So this is just something to bear in mind. It's quite useful in some sense, but it's quite difficult to spatially visualize. So it's not that big of a deal if you can't actually recall this whole equation. The important bit, I think, is this Cartesian equation, where the normal vector 1, normal vector 2, and normal vector 3 are essentially n components. So that would be n1, n2, n3 in 3D vector space. This n corresponds to this n, and the 1, 2, and 3 n's are the corresponding constants or values of the coefficients. So this equation will be heavily used. D is basically, if you expand this, because dot product can you can do dot and cross product like you break open brackets, as long as this is not a dot across. So r take a dot n will be r dot n minus a dot n, R dot n is essentially this n1, n2, n3 complex, and therefore minus a dot n will have to be d. So these are two equations for you to actually remember. So let's try to find the plane that contains points 0, 2, and 5, minus 1, 3, and 2, and 2, minus 2, and 1. So it's not easy, but it's kind of doable. There are two main approaches. The first approach is to use a more Cartesian method, and the second method is to use a vector approach. So in order to find the vector plane, you want to find the normal vector, which can be done using cross product. I'm gonna do both, but it's gonna take a while, so I want you to just take a look. So first up, let's do this with straight Cartesian. We can write down a few equations for this plane. One of them is, I didn't tell you in the facts section, you can actually define a vector plane R as the points that start from a particular point A at some distance lambda of a directional vector, d vector, at another arbitrary direction vector, I'll call it v. So this is essentially, if you move from the origin 0 to A, you get vector A. Then if A is on the plane, you can glide on the plane, and so the direction D and the direction V must be two directional vectors on the plane surface. So D and V will both be normal to the normal vector. In this case, as long as D and V lies in the plane, it doesn't really matter which direction it is, plus or minus, it doesn't matter, because the mu and lambda can compensate for that direction. So let's have a look. In this certain scenario, if I call 0, 2, and 5 point A, 1, minus 1, 3, 2 as B, 2, minus 2, 1 as C. So I've got 3 points. And we have dot, like point A, we can just use A, so we can define this as A plus some distance lambda of a directional vector from within the plane. By definition, these 3 dots lies in the plane, so if I take the difference between these two, the resultant directional vector will be on the plane. So let's do that. I'll take B, take A as D, add another arbitrary mu of, I'll take C, take A, so this is also a vector equation. Now we want to break this whole thing into a Cartesian description. So R is defined as x, y, z is equal to A, which is 0 to 5, at lambda lots of B take A, so let's do that. B take A, minus 1 take 0 is minus 1, 3 take 2, plus 1, 2 take 5, minus 3, add mu lots of C take A, so 2 take 0 is 2, minus 2 take 2, minus 4, 1 take 5 is also minus 4. With this, we can rewrite this whole thing R into 3 equations. So just take the x components. X is equal to minus lambda plus 2 mu. Y is equal to 2 plus lambda plus negative 4 mu, etc. So let's do that. Minus lambda plus 2 mu. Y is 2 plus lambda take 4 mu. Z is 5 take 3 lambda take 4 mu. Then this is simply just a 2-variable simultaneous equation we can rearrange and solve. To do that, first take x and y. We can add these two equations to eliminate lambda, which gives us x plus y equals to 2 take 2 mu. Then we can also take y and y take z equal to minus 3 plus 4 lambda. From these two, now we have enough information to solve. We need to find a relation between lambda and mu, so we can state that lambda, from rearranging the first equation, is equal to 2 mu take x. So with that said, we can now substitute this whole thing into y equals y take z equals to that, and so we have y take z equal to minus 3 at 4 lambda, so at 8 mu take 4 x. We can now we have an 8 mu that we need to get rid of, and turns out that 8 mu, if we multiply this by 4, actually no, we want to use this equation because we have a mu defined without the lambdas. So in order to get 8 mu, we multiply this whole thing by 4. 4x plus 4y is equal to 8 take 8 mu. Now we can add these two together to yield the final equation. 4x plus 5y take z equals to 5 take 4x. Now rearrange, we get 8x plus 5y take z take 5 equals 0, and this will be the equation. From this we can plug out the normal factor as 8, 5 minus 1, and this will be important for to note down that just write it on a piece of paper or something. Actually, I'll just leave this whole thing in the corner when I do the factor approach. Now for the factor approach, we want to find again the difference between any of these 3 dots. I'm gonna stick with B take A, C take A. So we have a minus 1, 1, and minus 3. This will be D, directional factor, and V is V is 2, minus 4, and minus 4. To find the normal vector between these two vectors, we take the cross product of these two. So let's do that. Do the determinant method, which again, if you are watching this in sequence, I suggest you jump to topic, I think, for some, I think it's topic 4. I'm gonna do this matrix things, and I'm gonna explain how to do the determinants. But for now, this would be a minus 4, take 12, lots of I, take some lots of j, that j would be a 4 plus 6, then add some k where the something is 4 take 2, and that would give me a normal vector of minus 16, minus 10, and 2. This will be my normal, and as I have said, the normal vector of a plane, magnitude doesn't matter because it's just a direction that we care of. So that we can actually call this our normal vector on the equation. So we have, remember we have r take a dot n equals to 0. We can put n here. We know that R is the effective plane and A is either one of these. I'll take 0, 2, and 5. And we can do this and we can show that it is 0, but I'm gonna do it. I'll put this in the form of the Cartesian to show that both of them are the same. So again, we know the Cartesian, from the Cartesian method we got n is 8, 5, and minus 1. This turns out to be just a negative 2 factor off. And if we put this into the Cartesian equation, minus 16x take 10y plus 2 plus some d equals to 0, where d is equal, this is 2z, where d is equal to minus a dot n. So let's find a dot n. A dot n is 0 times minus 16, give me 0, add 2 times minus 10, minus 20, and 5, add 5 times 2, which is 10, which goes to minus 10 in total. So plug that in as minus 10. And since everything is a multiple of 2, we can reduce it to minus 8, minus 5, add z, take 10 take 5 equals 0, which is just the negative of the previous answer, which again will be the same. So actually I think I got a 10 off somewhere. Let's see if I do that. Oh yeah, of course. This is just a dot n, so I need to take a negative of this, which should give me plus 10 instead, so it's add 5, which now is the negative of the previous 8x plus 5y take z take 5 equals 0. So this is the exact same plane from using different methods. So tips for doing vector planes: make sure you know different ways of writing down a vector plane, that is. The vector form is helpful, but I feel like for A-levels it's more applicable to completely know the Cartesian method. So if you don't know the vector methods, I wouldn't be too worried. I would be slightly worried, but not very much. As long as you know exactly how to do Cartesian methods, then you should be set for any question they throw at you. And also, it's important to practice the cross product, because in the coming exam, factors in vector cross product is useful in a lot of situations. To find the normal vector cross product come into play a lot, and even in future applications, when you get into a kind of science that requires you to do vector fields, for example physics or some engineering stuff, then these vector stuff that you're learning will very much come in handy. So it's time again for doing some practice questions. I have set 2 questions for you today. First one is just find the normal of this equation, this plane in 3D space. And question 2 is to find the plane that contains these 2 directional vectors and the point, the origin. So I'll give you 5 seconds, pause the video if you need to, and do attempt these questions. Practice makes perfect. So I'll reveal the answer in 5, 4, 3, 2, 1. So these are the answer. And question 1 is actually really no-brainer. You literally just copy out the coefficients of x, y, and z. So do not, like when I say do not put in too much thought, you do need to think, but do look out, because Cartesian coordinate is really helpful when talking about normal vectors. And we'll surely go in a bit deeper with this Cartesian normal in the coming videos. And question 2, cross product, that's what I'm gonna use pretty much every single time, because that saves you a lot of algebra. It basically just makes it a lot less likely that you're gonna make algebraic mistakes. You can put it in 2 forms. I prefer the Cartesian kind of expression, but in the exam you are completely allowed to leave it in vector form. I would write this in column vector though, just to make the examiner happy, I guess. So with that said, this will be the end of the video. I hope you've learned something. If you have any questions, do leave me a comment in the comment section below, and I will see you on my next one.